In this video, I look at some cross-assemblers that support the Heathkit H89 and related computers. In a previous video, I talked about cross-compilers, which run on a host computer and can generate code for a target computer system. In a similar vein, cross-assemblers can build assembly language programs on a host computer intended to run on a target system. As with cross-compilers, they can benefit from the processing power of a more powerful host system than the target. The Heathkit H8, H89, and related computers offered native assemblers, either running standalone on a cassette or paper tape-based computer or under Heathkit's HDOS operating system. The Heath assembler was well documented in the Heathkit manuals and supported the Intel 8080 processor, which was used on the H8 and compatible with the Z80 used on the H89. I wanted to build some of the Heathkit code, most notably the firmware for boot and monitor ROMs, on a modern computer to help understand the code and potentially modify it. I also wanted to write new code, primarily for HDOS. Heathkit published full source code listings for most of their ROM code. In searching for a suitable cross-assembler, the Heath assembler had a number of features that ideally a cross-assembler would support. First, Heath often used split octal numbers in the code, so ideally the assembler would accept these and display them in source listings. The assembler supported a number of directives, some of which were unique, such as xtext for include files, and a macro facility to support things like system calls and assembly time error checking. I also wanted the cross-assembler to run on a Linux system, as that's my primary development environment. Here's an example of the Heath published listing for a small demo program that was published in the Heath manuals. And here's the assembler output I got from the native Heath assembler under HDOS. AS or ASL is a portable macro cross-assembler for a variety of microprocessors and microcontrollers written by Alfred Arnold. I had earlier used the ASL assembler on some other platforms and found it worked well. I was hooked when I discovered that it had support not only for octal but for split octal in listings. This was ideal as I wanted to be able to compare the assembler output with the Heath published listings. There are incompatibilities with the Heath assembler which need to be handled in various ways. Source code comments need to use a semicolon rather than an asterisk. Some assembler directives like xtext for include files need to be changed, in this case to include. System calls and some other functions need to be handled by defining suitable macros. While octal constants are supported, there's no support for split octal constants, so these need to be changed to octal or hex. I also found use of a few alternate names for 8080 instruction mnemonics that could be handled by changing the code. Given these differences, it wasn't difficult, although somewhat time-consuming, to take the Heath source code and port it to the ASL assembler. The final result was binary code that exactly matched the Heath ROM images. It's very fast. I can build a dozen programs on my Linux laptop in well under a second, with each assemble taking 0.01 to 0.03 seconds. Here's the assembler listing for the demo program with output in split octal. In the case of HDOS, to generate HDOS executable ABS files, I wrote a small Python script that takes a raw binary file generated by the assembler and adds the small 8-byte header required by HDOS. One additional issue I found was that while most H89 code uses 8080 instructions for compatibility with the H8 computer, some of the H89 firmware occasionally uses some Z80 instructions for efficiency. It appears that the Heath assembler had support for some Z80 instructions. A nice feature of ASL is that you can change CPUs on the fly in the source code, for example from 8080 to Z80 and back. I made use of this feature to handle this when it came up. Unknown to me when I started working with the ASL assembler was that well-known Heathkit user Mark Garlanger had taken the code for an open-source assembler called ASMX and modified it to support most or all of the Heathkit assembler features. This includes the same basic rules for source format, including comments, split octal constants in source code and in listings, assembler directives such as xtext for include files and scall for system calls, and alternate instruction mnemonics used by Heath. I recently started using it and it worked very well. For example, Heath published a small demo program for the H88 in one of their manuals. I was able to assemble it with ASMX without making any changes to the code in the manual. Here's the assembler listing, which is almost identical to the Heath assembler's output. Mark Garlanger has assembled much of HDOS 3.0 using the assembler in order to test it. I may port my source files to it at some point, which will mostly be a matter of reverting the changes I had made to port it to the ASL assembler. I've shown here a couple of cross assemblers that can be used to build Heathkit H8 or H89 assembly code on a modern computer. Using a cross-assembler can speed up development time and make it more convenient. Even Heathkit used a cross-assembler for much of their development, as some of the published source code listings show an assembler that was running on a Unix computer. Shown as Unix H8 ASM, it probably ran on a DEC PDP-11 mini computer. I focused here mostly on HDOS as it's the most challenging to support. Under the CP/M operating system, an assembler was also included as part of the operating system. There are a number of 8080 cross-assemblers that are compatible with CP/M's assembler, which I didn't attempt to cover here.